Welcome back to eCoreAcademy, everyone. My name is Anita and I am one of the teachers and co-founders here, along with my younger brother, AJ Raj. As you can see today, we have a new Algebra 2 lesson, and we're going to be continuing our lesson on rational functions and their graphs. As I said before, this was a topic that was requested by some students in India who are preparing for their exam, and this is going to be our second part of our lesson in this rational functions and their graphs mini series. So the first one was an introduction, so I highly suggest you go check that out before you come to this one. This lesson is going to focus all on discontinuity. Discontinuity is a topic you go over extensively in pre-calculus, especially if you're in pre-calculus honors. And at the end of the year, they'll integrate a calculus unit into pre-calculus where you learn all about limits and continuity and discontinuity. So you talk more about it next year in pre-calculus, but it does come up in rational functions, so I do want to focus on that. Obviously, we're not going to be looking at it as in-depth as a pre-calc student would, but you also need to understand how does discontinuity play a role in the graphs of rational functions. So today what we're going to focus on is we're going to understand what the words continuous and discontinuous mean. We're going to define both of them, and then by defining them, you'll be able to tell what are the differences and what category do rational functions fall into, because they can fall into either one depending on the rational function you're looking at. We're going to determine what those terms mean, and then we're also going to practice determining where discontinuities are if the rational function has them, just by looking at the equation of the rational function. We're not even going to need a graph for this, so that's why I said without having to graph. So without even having to graph, just by looking at a rational function, we're going to learn how to identify where the points of discontinuity are. So that's the purpose of today's lesson. Before we get into the lesson, I just want to show you this image I put up here. You see two people clapping, and it says asymptotic high fives. So we talked about asymptotes in our last lesson. They're a type of discontinuity. It's pretty much a line that the curves of your function will approach, but will never touch that line. They just continue approaching that line until infinity, but they will never touch it. And it's a kind of discontinuity because it's a vertical line, so the equation of the vertical line is x equals some constant. It doesn't have a defined slope, and at that x value, there is no y-coordinate for the rational function because the rational function will never even touch that vertical line, meaning it doesn't even have a y-coordinate at that x-coordinate. So that's a type of discontinuity, and as you can see here, in some instances, we have vertical asymptotes. In this case, our vertical asymptote is the y-axis, so it's x equals 0. You see two people clapping, so it kind of represents the curves of a rational function. So that's why it says asymptotic high fives. Sometimes you'll see rational functions that approach their asymptotes like that. And also you'll see that there's a horizontal asymptote incorporated into this, but don't worry about that. We'll talk about that in 2 more lessons. And before I get into the lesson, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. All right, so let's understand what continuous versus discontinuous functions are. Let's define some terms and then look at an image that I hope will clarify some of these terms for you. So what does continuous mean? So continuous means you're representing a graph that has no jumps, breaks, or holes. So we talked about breaks and holes in our last video. Breaks are where there's no defined point at a specific x-coordinate for a function, and the breaks we looked at are vertical asymptotes. As I said before, vertical asymptotes are where a function's curves will approach a vertical line at a given x value, but they'll never touch it. So for that x value, the value of the function is undefined, and you'll have vertical asymptotes when the denominator is equal to 0. So it's not always the case with rational functions, but usually you'll see vertical asymptotes with rational functions. And then you have holes. Holes occur where you have a rational function. Remember when we said rational functions are defined as f of x equals p of x, which is your numerator, divided by q of x, which is your denominator, both of which are polynomials. When you divide p of x by q of x, sometimes p of x is going to be, for example, a quadratic trinomial. And then you're going to have q of x as a linear binomial. And you'll actually be able to factor p of x using something like the guess and check method, and you'll see that q of x actually divides into p of x, meaning there's a common factor between the numerator and denominator. So you'd obviously cancel that out, and usually for our purposes we were left with a linear equation. We can't just ignore the common factor we canceled out. Instead, there's going to be a hole there, so you would set that common factor equal to 0, determine what x is, and then there's going to be a hole at that value. So that's another kind of discontinuity, because there's no defined point at that x value for the function. We also have jumps. You're going to get more into jumps next year with pre-calculus, but in my experience as a pre-calculus student, we saw jumps with absolute value functions. So I'll show you a diagram, but for our purposes, you don't need to worry about that. Now, what's discontinuous mean? So discontinuous means that we're representing graphs that contain jumps, breaks, or holes at x equals some value a. So it's like the complete opposite of the definition we went over for continuous. So all those things that I just mentioned, the vertical asymptotes, the holes, the absolute value functions with the jumps, those are all, as long as we don't have those things, we have a continuous function. Continuous function has a corresponding y-coordinate for every x-coordinate. It's constant. There are no breaks. It's just, if you look at the function from left to right, every single x value has a corresponding y value. There's a point for every x-coordinate. However, discontinuous is not the same thing. This is where we have those jumps, we have those breaks, we have those holes. We have areas in the function that are going to be split that don't have a corresponding y-coordinate for an x-coordinate. For example, with the asymptote, we just have this vertical line which consists of infinite points at an x value, but the function is not even defined at that x value. If a function is not defined at every single x value, then it's not continuous, it's discontinuous. So at that vertical asymptote, because it just approaches the vertical asymptote but never intersects or touches it, there is no corresponding y-coordinate at that x-coordinate, so it's not a continuous function. It's discontinuous. Same thing with holes. Every single x-coordinate needs to have a corresponding y-coordinate for the function to be continuous. But when we have holes, we have a x-coordinate, but the y-coordinate we do have a y-coordinate, but at the same time, because of that common factor, we have to put a hole in the function, so it's technically not a defined point. That is part of the function. So that also is a undefined point, so it's a discontinuous function. And then again with the jumps, what happens with the jumps are, you'll get into this next year, but there's something you do called the continuity test. So you'll be given a function and you'll have to determine if it meets 3 specific criteria. The first criteria is, does the function have a limit? And a limit you'll learn about next year and you'll talk about more in calculus. But a limit occurs when you're trying to understand what value does the function approach as the input approaches a specific value. So for example, as the input or x value approaches 2, I'm just making this up, what value does the function approach? So when we say value of a function, we mean the y-coordinate. So as x approaches a specific value, what value does y approach? So that's what we are trying to determine when we talk about limits. And when we have jumps, you'll have I'll show you an image, but you'll have a function, but then what happens is, as the function from the right side, so we call that the right limit, the right-sided limit, and then the function on the left side, which is the left-sided limit, sometimes they will approach an x value, but they'll approach 2 different y values. And what happens is you'll have like this little gap between the 2 different coordinates, and it's called a jump because you have to jump from one point to the other. Those are discontinuities. A jump is considered, so we have 4 different types of discontinuities you study in pre-calculus, and I'll go through this quickly. A jump is simply called a jump discontinuity, and these breaks are called infinite discontinuities. For our purposes, we've been associating breaks with asymptotes, specifically vertical asymptotes. And if you saw, the vertical asymptote is a vertical line, the curve is approaching that line, and it's just going to continue towards infinity. Whether it increases or it decreases, it's going to continue towards infinity without ever touching that vertical line. We call that increasing or decreasing without bound. Without bound means there's like literally no restriction. It's just going to keep going towards infinity. That means it has no limit because usually it approaches 2 different values, or it usually approaches 2 different values as x approaches that value where the vertical asymptote occurs. If it approaches 2 different values, that means the function from the right, or the right-sided limit, is going to be increasing or decreasing, while the function from the left is going to be increasing or decreasing. So it's going to go in the opposite direction. But if they're both going in the same direction, let's say the function is increasing from both sides or it's decreasing from both sides, well, they don't have a defined point at that x value, so it's still a discontinuous function. The graph is said to have a point of discontinuity at x equals a. So again, a was that constant we were talking about. When the graph is said to have a point of discontinuity, that's what a hole is. A hole is considered a point of discontinuity because unlike infinite discontinuities are vertical asymptotes. An asymptote is a line, and a line has an infinite amount of points. However, when you have a graph that has a single point of discontinuity like a hole, there's only one place where the function is undefined. Not undefined, but doesn't have a corresponding y-coordinate, so that point is undefined. There's only one place. There's not a whole line. There's just one place. So the graph is said to have a point of discontinuity at that one point where x equals the constant a, which is the common factor between the numerator and denominator of the rational function. And then later in pre-calculus, you'll also learn about oscillating discontinuities. You don't have to worry about that now, but I will talk about it a little bit as we go through this image. So the first image you see is a removable discontinuity, which is right here. So as you see, there's a graph. This is this is a. So this is where x would equal a, as you can see, because that's on the x-axis. And this is just a line, a linear regression, a linear equation. But as you can see, there's an open circle at a. And that means that there's a hole at A. And they call this a removable discontinuity, and we'll talk about why it's called a removable discontinuity. It's also called a point discontinuity, because as you can see, the rest of this function is continuous, but at this one point, it is discontinuous because this x-coordinate doesn't have a corresponding y-coordinate. It's an undefined point. So that's why there's an open circle. It occurs because of that common factor. Then you have the infinite discontinuity. Here we have our vertical asymptote. We also have a horizontal asymptote, which we'll talk about later. But as you can see, this line over here, this is the limit from the left, or the left part of the function. It's going to be increasing without bound. It's just going to increase towards infinity without ever touching this vertical asymptote. So it's never going to, the function's never going to have a corresponding y-coordinate when x is equal to a. The same thing goes for the right side of the function. This part of the function is going to be decreasing without bound infinitely without ever touching this vertical line. So it's never going to have a corresponding y-coordinate as x equals a. And as you can see, this function's approaching two different values as x approaches a. Then we have our jump discontinuity. In this case, it's not an absolute value function, but as you can see, this is more of a piecewise function. And you hopefully remember that from Algebra 1. This part, as you can see, it almost looks like half of a parabola, and this part looks like a line. But the thing is, at x equals a, this line approaches a at a different y value. It approaches it up here in quadrant 1, whereas this function approaches a at a different y value in quadrant 4. And as you can see, I can literally jump from one value to another, so that's called a jump discontinuity, where the limit from the left is not equal to the limit from the right, so the function's approaching two different values from the right and the left. That's another kind of break in the function. Lastly, we got the oscillating discontinuity. As you can see, it's kind of like a wave. We call this a sinusoidal wave, and you'll learn about it when you talk about trigonometry and pre-calculus. So the wave is pretty much the parent function of y equals sine of x, and you'll go into graphing trig functions later, but that's where you get the wave from. And when you have an oscillating discontinuity, what happens is the function is approaching two different values simultaneously. So as you can see, there's a bunch of different waves clumped together. It's almost like a high frequency radio or a wavelength. So they're all clumped together, really close together. So you can't even tell what value, what y-coordinate corresponds to the x-coordinate a. So because you can't tell, this is another kind of discontinuity. All right, enough of that. Let's get into previous examples. Hopefully you recognize these three graphs from the last video. This was our first graph we looked at, second graph, and then the third graph. Here's just a graph, and then here's another graph, but as you can see, it's a line with a hole in it. And then here we got a function, but it has a vertical asymptote at x equals 2, and the hole here is at x equals negative 2. So hopefully you remember these graphs. Well, now let's label them as continuous or discontinuous based on what we've learned in the last slide. So let's look at graph A here. Well, are there any kinds of breaks? So I know, before I get into this, I just want to say, I know I went into a lot of detail on the last slide, but as an Algebra 2 student, don't worry too much about, oh, what kind of discontinuity is this, or limits, or anything like that. I'm just giving you that information for those of you who need more information to better understand a topic. But as an Algebra 2 student, all you have to do is just look at the graph along the x-axis, because we're focusing on, does every x-coordinate have a corresponding y-coordinate? And if you look along the x-axis and you see that there's a break where an x-coordinate doesn't have a corresponding y-coordinate, whether this be due to a hole or an asymptote, because those are the two types of breaks we will be working with in this unit specifically, that's when you can tell that a function is discontinuous. You don't have to do a continuity test or all those other things that you'll have to do next year. All you have to do is just observe the domain. So we're going to be looking at this function from left to right. And as you can see, every x-coordinate has a corresponding y-coordinate. This function has points for every single x-coordinate. Therefore, graph A is continuous. Remember, we talked about how this would have a vertical asymptote at x equals plus or minus I. I didn't show you the equation of this graph, but I remember we talked about it in the last video. But because we're graphing on the real number plane and those are imaginary numbers, this technically does not have any discontinuities. Let's look at this graph. We have a linear regression, but we have a hole at x equals -2. So the domain is defined for every single point, except when we get to x equals -2, it's an open circle, meaning it doesn't have a corresponding y-coordinate. The function doesn't have a value at this point. Therefore, graph B is discontinuous because of this hole that interrupts the domain. Now let's look at this function over here with the vertical asymptote at x equals 2. I think this one should jump out to all of you. This is going to be an infinite discontinuity if we want to use terminology from calculus. But for our sakes, you can just think of there's a break in the graph. There's a break, and that occurs at the vertical asymptote at x equals 2. So the domain is fine. It's defined for every value of this function until we reach x equals 2. In this case, we don't have a y-coordinate. We just have these two curves approaching the vertical asymptote, but they never touch it. Therefore, graph C is also discontinuous. Alright, so now we're going to get into some examples of finding discontinuities, like I told you, just using the equations of rational functions, but without having to graph the rational functions. So the instructions are, find the points of discontinuity for each rational function that I show you, and then we're going to state if they are removable or non-removable. So if they are non-removable, that means there's a vertical asymptote at that point. So that means there's a break at that point. And remember, we can tell if there's a vertical asymptote while keeping in mind that you're determining when the denominator equals 0. So to determine if there's a vertical asymptote, we set the denominator of the rational function equal to 0, and then if x equals some constant value, then we determine that is where the vertical asymptote is. It is non-removable because, as I say here, removable discontinuities are when something cancels out. That means we have a hole and there's a common factor between the numerator and denominator. When those cancel out, that means you have a hole in your function. And when you have a hole in your function, you only have a single point of discontinuity. And that one point, what happens is, remember how I talked about how that was also referred to as a removable discontinuity. Point discontinuities can have their functions redefined or rewritten. You'll learn more about that in calculus, but they can have their functions rewritten so that there's a point that's added to the function to make the function continuous. So that's why we consider, when we have a hole in a function, we consider that a removable discontinuity. However, when you have a vertical asymptote in a rational function, that's a whole line, so that's infinite amount of points. However, when we redefine a function, we can only redefine a single point. So that's not going to solve the problem of a vertical line that has an infinite amount of points. So that's considered a non-removable discontinuity. So what we're going to do is we're going to determine what kinds of discontinuities these functions have. We're going to set the denominator equal to 0 to find out if we have any vertical asymptotes. Then we're going to see if there are any similarities between the numerator and denominator, so we can see if there are common factors that cancel out and give us holes. Okay, so here's our first example. We have the function f of x equals x plus 3 divided by x squared minus 4x plus 3. The first thing we want to do is set the denominator equal to 0 to see if there are any vertical asymptotes. So we set x squared minus 4x plus 3 equal to 0 in the denominator. And then what we're going to do is we're going to factor this because it's a quadratic trinomial, and we can factor it by the guess and check method. So we're going to factor into x minus 1 times x minus 3, and we're going to set that equal to 0 just as we did the original quadratic trinomial. Then we're going to take each of these factors and set them equal to 0, just like when we were solving for quadratics. So we're going to set x minus 1, which is the first factor, equal to 0. So x minus 1 equals 0. Add 1 to both sides to get x equals 1. Do the same thing with x minus 3 equals 0, and then add 3 and you get x equals 3. There are no similarities between these factors, x minus 1 and x minus 3, if we compare them to the numerator, which is x plus 3. These two factors are different from the numerator, so there are no similarities or no common factors. So we're not going to have any holes. These here, x equals 1 and x equals 3, are going to be our vertical asymptotes that we found. And remember, vertical asymptotes are non-removable. The next example, h of x equals x minus 5 divided by x squared plus 1. So first we're going to set the denominator equal to 0 to find our vertical asymptotes. X squared plus 1 is equal to 0. If we subtract 1 from both sides, we get x squared equals negative 1. And then if we square root both sides, we get x equals positive or negative I. Because remember, in the real number system, you can't square root a negative number. But because we've already learned about imaginary numbers, I decided to take it a step further and show you that when we square root negative 1, we get I, but we can get positive or negative I, which is the principal or negative square root. So you can take, when you square root a number, you can take the principal or the positive square root or the negative square root. So in this case, x is equal to positive or negative I. However, you can see that I wrote no discontinuity because, again, for our purposes with rational functions, we are graphing on the real number plane. So there's no way we would graph an asymptote x equals negative I or x equals positive I on a real number plane. We can do that on an imaginary number plane, but we're not working with an imaginary number plane. Therefore, there is an asymptote there at x equals positive or negative I, but because we're on the real number plane, there is no discontinuity at all. Now let's look at t of x equals 1 divided by x squared minus 16. We want to set the denominator equal to 0 first, so we do x squared equals 16 and set it equal to, x squared minus 16 is equal to 0. Then we're going to add 16 to both sides to get x squared by itself, so we get x squared equals 16. Then we're going to square root both sides, and when you square root 16, you get 4, but you have to take the principal or positive root and the negative root. So we get x is equal to positive or negative 4. As you can see, the numerator is 1, and then what happens is when we simplify this, we get positive or negative 4. So we already know that there's going to be no common factors between the numerator or denominator, so there's going to be no holes in this. So we end up getting this answer as the two vertical asymptotes. So there's x equals negative 4 as one of them, and x equals 4 as the other vertical asymptote. Because they're vertical asymptotes, they are non-removable discontinuities. Here's our last example. S of x is equal to x squared minus 3x minus 4 divided by x minus 4. So the first thing we want to do is set the denominator equal to 0, so x equals 4 equals 0, x minus 4 equals 0, and then we add 4 to both sides, and we get it equal to x equals 4. The thing I want you to notice that we did was we factored the numerator next, because it's a quadratic trinomial, and we want to see if there's a common factor between x minus 4 and the numerator. So we set x squared minus 3x minus 4. We factor that using guess and check, and we get x minus 4 times x plus 1. Both of these instances, we're dividing by x minus 4 to see if there's a common factor that will cancel out. And in our case, there is. So these x minus 4s in the numerator and denominator are going to cancel out, leaving us with just an x plus 1. That means that this here that we found here, there is no vertical asymptote because this was actually a common factor. We're left with this as our simplified function, so we can actually rewrite the function as this. But when we graph, we have to make sure we include a hole at x equals 4 because, again, we factored the numerator. We got a common factor between the numerator and denominator. So instead of having a vertical asymptote, now we got a hole. So we have a hole at x equals 4 because we set x minus 4, which is the common factor, equal to 0. Find that x is equal to 4. So we find x is equal to 4, and because it's a hole, it's a removable discontinuity. So in our second example, we're going to continue finding discontinuities. We're going to determine the points of discontinuity, and then we're going to determine the types of discontinuity. So we're going to say if it's a hole or a vertical asymptote, and if it's a hole, we're not just going to say x is equal to some constant. We're going to plug x into our new function, our new simplified function, to provide a coordinate pair by getting a y coordinate. So let's look at our first example. Y is equal to x minus 4 times x plus 3 divided by x plus 3. So first, we're going to set our denominator to equal to 0. That's what we always do. So we're going to set x plus 3 equal to 0 and subtract 3 from both sides to get x equals negative 3. Then we're going to see if there are any common factors between the numerator and denominator. So we're going to do x minus 4 times x plus 4, x minus 4 times x plus 3 divided by x plus 3. And you can see that there's a common factor of x plus 3. So those will cancel out and they will leave us with x minus 4, which is like our simplified function. However, we can't just ignore the x plus 3 we canceled out because we know that there's a hole there. There's no vertical asymptote, but there's a hole there. So what we're going to have to do is we're going to take this x equals negative 3 that we found and plug it back into x minus 4 to find the corresponding y coordinate, because the instructions tell us to give our answer as a coordinate pair, not just x equals negative 3. So we're going to plug x equals negative 3 into x minus 4, and we're going to get negative 3 minus 4 equals negative 7. So we're going to write our discontinuity as the point negative 3, negative 7, and we're going to say that there is no VA. VA stands for vertical asymptote. It's just an abbreviation because I know writing out vertical asymptotes a lot, so you can just abbreviate it that way. Now we have the function y equals x minus 3 times x plus 1 divided by x minus 2. We're going to first set the denominator equal to x minus 2, equal to 0. X minus 2 equals 0, add 2 to both sides, x equals 2. If you compare the numerator and denominator, we already have everything factored for us. We don't need to factor anything. And you can see that all of these factors are different. So there's no common factor between the numerator and denominator. There's no x minus 2 in the numerator, so there's no common factor, no similarities. So this x equals 2 that we found, it's just going to be a vertical asymptote. It's not going to be a hole. So x is equal to 2. And remember, we give vertical asymptotes. We're not giving a specific coordinate pair because it's actually an entire vertical line, and a line is an infinite amount of points. So we're going to write our answer as x equals 2, and we're going to say that there are no holes in this function. Our next example, y equals 2 divided by x plus 1. First step, set the denominator equal to 0, x plus 1 equals 0, subtract 1, and x is equal to negative 1. There's no common factor between 2 and x plus 1, so there are no similarities, no common factors, meaning there are no holes. Our only discontinuity is this x equals negative 1, meaning this is a vertical asymptote. So our discontinuity is x equals negative 1, and there are no holes in this function. And our last example, y is equal to 4x divided by x to the 4th plus 16. So we're going to set the denominator equal to 0 first. So x to the 4th plus 16 equals 0. We're going to subtract 16 from both sides. So x to the 4th equals negative 16. And keep in mind that whenever you have a positive power, so in this case even power, when x is raised to the 4th is a even power. And when you have an even power, just like squared, you can't square root or take the 4th root of a negative number. So at this point, we're going to get x is equal to 2i, because 2 to the 4th is equal to 16. So if we have 2i to the 4th, that's going to give us negative 16. And this is going to be positive or minus because of the principal or negative root. So this is not a real answer. I want you to keep in mind because I is not a real number. And again, we're graphing on the real number plane. So technically, this answer is void. So there is no vertical asymptote. And you can also see there is no common factor between the numerator or the denominator. So there are no vertical asymptotes and there are no holes in this function. Okay, we're going to go through our last 4 examples, continuing to find discontinuities. And our only instructions are find any points of discontinuity for the rational functions below. So here's our first function, y is equal to 3 divided by x squared minus 16. We're first going to set the denominator equal to 0. So x squared minus 16 is equal to 0, and we're going to factor this. This is a difference of squares. I don't know why I blanked out for a second. This is a difference of squares. So if we do a difference of squares as we learn, so a squared minus b squared is equal to a plus b times a minus b. So we're going to factor this to x plus 4 times x minus 4 is equal to 0. We take each of these factors and we set them equal to 0. We get x plus 4 is equal to 0. And if we subtract 4, we get x equals negative 4. We do the same thing with x minus 4. X minus 4 equals 0. Add 4 to both sides to get x equals 4. So our two vertical asymptotes are going to be x equals negative 4 and x equals 4. Because we don't have a common factor between the numerator, which is 3, and the denominator, which is x squared minus 16, there are going to be no holes. So our only points of discontinuity are x equals negative 4 and x equals 4, which are both vertical asymptotes. Our next example, y is equal to x minus 1 divided by x squared plus 2x minus 8. So let's set the denominator equal to 0. X squared plus 2x minus 8 equals 0. You can factor this quadratic trinomial to x plus 4 times x minus 2 and set that equal to 0. Then you're going to set each of these factors equal to 0. And before we do that, I want you to notice that since we factored the denominator to this, you can see that x minus 1 has no common factors with the numerator. X plus 4, x minus 2, and x minus 1 are all different factors. So there are going to be no holes here. So we're going to set x plus 4 equal to 0 first, subtract 4 and get x is equal to negative 4. We're going to set x minus 2 equal to 0, add 2 to both sides, and get x equals 2. And our two vertical asymptote discontinuities are going to be x equals 4, negative 4, x equals negative 4, and x equals 2. Our next example, y is equal to x minus 1 divided by x squared minus 4x plus 4. First, we're going to take our denominator and set it equal to 0. So x squared minus 4x plus 4 equals 0. If we factor x squared minus 4x plus 4, we'll end up getting x minus 2 times x minus 2 equals 0. And you can see that this is a perfect square binomial. In this case, it is a squared minus b squared, a squared minus 2ab plus b squared. So that is our perfect square binomial. If you have a perfect square binomial, you only have one solution because these two factors are exactly the same. So x minus 2 is equal to 0, and so you set only one of these equal to 0 because you're going to get the same answer if you set both of them equal to 0. They only have perfect square binomials only have one solution. So x minus 2 is equal to 0. If you add 2 to both sides, you get x equals 2. Because x minus 2 and x minus 2 have no common factor with the numerator, which is x minus 1, there are no holes. There's just a vertical asymptote. So our vertical asymptote is at x equals 2. And our last example, y is equal to x minus 1 divided by 5x squared minus 25. Set the 5x squared minus 25 equal to 0, and you can actually factor out of 5. So if you factor out of 5, you can get 5x squared divided by 5, so we get that x squared, and you can divide 25 by 5, and you get this minus 5 here. So you factored the 5 out, and then you divided both sides by 5. So 0 divided by 5 is just equal to 0, so you get rid of that extra 5. Then you're going to get x squared minus 5 equals 0, and you're going to add 5 to both sides, so you'll get x squared equals 5. Our final step is to just take the square root, and x is equal to the positive principal or negative square root of 5. 5 is not a perfect square, so we're just going to leave it under the radical. So in this case, you can see that there are no common factors between the numerator and denominator, so these are vertical asymptotes. We're going to have two. One is going to be x equals the negative square root of 5, and then the second one is going to be x equals the principal or positive square root of 5. And that's all for today. I hope you enjoyed the video and stick around for the next video where we're going to get into graphing, which I think a lot of you will look forward to. If you enjoyed the video, please like, subscribe, hit the post notification bell, and drop a comment down below. Also, share using our socials, check out our website, and email us at our Gmail with any inquiries. Thank you for watching, and see you next time.